I want to teach you guys, okay, about electrode potential. Okay, electrode potential. Do remember when you have electrolysis, okay, you are going to have, okay, the movement of electron, and this movement of electron is going to happen in the wire. Yeah, so don't actually think that the electron will swim its way in the electrolyte and then so on. Okay, they do not get conducted that way. Okay, that one, okay, if it is within the solution, then we are talking about the movement of ions. Okay, so do remember the movement of the electron is always going to happen in the wire itself. Yeah, the external circuit. Yeah, so we have, okay, there will be electron loss and there will be electron gain. So we can have a redox equilibrium, yeah, because this electrolysis is a redox reaction. Oxidation and reduction will take place. Now we know, okay, in the past when we learn about electrolysis, okay, we know that, okay, we have unreactive metal, we have reactive metal. That's why you have the reactivity table, and then we predict which one is more reactive and which one, and then we can predict which one is going to be discharged and so on. Okay, now, okay, I give you one example. Okay, one example is going to be copper. Okay, another example here is going to be vanadium. Now, if I compare copper and vanadium, no need to memorize. But if I tell you, yeah, copper and vanadium, vanadium is more reactive. Okay, you do not need to memorize anything. Just think, yeah, this one is going to be more reactive. And the clue that I can give over here is vanadium and copper, they are both metals. Okay, now when it comes to metals, Ashley, when it comes to metals, when I say something is reactive or not, metals, they have tendency to lose electron or gain electron.
Tendency to lose electron.
Okay, all metals, when we say reactive, it means we are talking about tendency to lose electron. You can refer to like maybe group 1, group 2, yeah, they have 1 or 2 valence electron, they have tendency to lose electron. So if I say vanadium is more reactive than copper, it means that vanadium has tendency to lose electron more compared to copper. Yeah, so it means if I write the equation, vanadium, okay, will lose the electron. Okay, so it depends on what they are going to form. You see, it's going to be 2 plus, so it means they will lose 2 electrons. Okay, to give you vanadium 2 plus. But in chemistry, we don't write minus 2 electron. Okay, we write, okay, we bring this minus 2 electron, we bring it over here. It's going to be plus 2 electron. Okay. And then if I have copper, okay, copper will lose the electron also, okay, to give you copper 2 plus and 2 electron. But if you compare these two equations, okay, because we know vanadium is more reactive than copper, it means that this reaction is going to be more favored. Okay, it means vanadium, okay, will be giving you electron. Okay, tendency to give you electron is more compared to copper. Okay, this is very important. And I told you that, okay, redox equilibrium is going to be achieved. It means, okay, redox equilibrium means the reaction is going to happen. Okay, there is oxidation and there is also reduction. So we can actually represent this, okay, in this way. Okay, it means there's another one more reaction that can go this way. Yeah. So if you look over here, when I say this is going to be a reversible reaction, and we have learned about, okay, the position of the equilibrium. Now, if I want to compare the position of the equilibrium, okay, if I want to compare, we supposed to be everything, the position supposed to be in the middle. But now, because vanadium is more reactive, okay, Clienta, can you predict if vanadium is more reactive, do you think the position of the equilibrium, according to the equation that I've written over here, do you think it's going to be to the right or to the left? If I say vanadium is more reactive, or no change?
To the left.
To the right. Okay, correct. okay, the position of the equilibrium is going to be to the right. Why? Because, okay, we know that vanadium is more reactive. Of course, they are going to give you more electron. Okay, it means they are going to be, the position is going to the right. Okay, so the position of the copper, okay, this equation is going to be more to the left in this case, in this equation. Okay, so using this concept, okay, we are going to apply, okay, over here. But in this chapter, okay, you need to make some adjustment. What is the adjustment? We are going to use, if you look at the data booklet, okay, the data booklet, it's all written in form of equation, but they use standard reduction potential. Okay, standard reduction potential. Now, what is standard reduction potential? If you don't know about that, it's okay. Let's focus on the term reduction. Yeah. So, Dylan, what is reduction?
Gain of gain of electrons.
Okay, reduction is gain of electron. Yeah? Oil rig. Oxidation is loss of electron. Reduction is gain of electron. It means when you look at your data booklet, they write standard reduction potential. It means they will write the equation in terms of gaining electron. But when you look at the way that I have written over here, it is written in form of losing electron. So what is the adjustment that we need to do over here is to change this equation the other way around. Copper 2 plus 2 electron to give you copper. Vanadium 2 plus 2 electron to give you vanadium. It means you just need to rearrange the equation to make the electron to the left, because it will look like this one add with electron, this one add with electron, gaining electron. So we want in reduction form. And the concept is still going to be the same. If this one is moving to the right, it means they are forming V2 plus. Okay, it means the position of the equilibrium over here is going to be to the left. If I write this equation, if copper, okay, if I say it's going to be the position of the equilibrium is towards copper, so it means this one, the position of the equilibrium towards copper is still the same. Yeah. So it's the same concept. Okay. It's still the same concept. Okay. But let's go deeper into it. Okay. Now you see here for unreactive metal copper, the equilibrium lies further to the right. Why? Now from now on, okay, we will write using this reduction equation. It means we are going to forget about the way that we write in terms of losing electron. So I'm not interested with this anymore. Okay. So if they say this is going to be unreactive, unreactive means what? Copper do not give you electron. If copper do not give you electron, it means that they are not going to give you electron. They are not going to give you electron. So they are not going to go there. Okay, copper is not going to give you copper 2 plus and copper 2 electron. So that is going to be the situation over here. So the equilibrium is more to the right. And if you look over here, copper 2 plus, what can you say about copper 2 plus? Copper 2 plus, okay, you see what is happening in copper 2 plus. They are going to have, okay, reduction is gain of electron. Okay, it means that copper 2 plus have ability, okay, to gain electron more. Okay, you can see from the direction of the equilibrium. It means copper 2 plus have tendency to receive the electron to form copper. Yeah, so it means that copper 2 plus is more easier to reduce. Why more easier to reduce? It can gain electron more. Why? Because the position is shifted to the right. Okay, and if you compare with V2 plus, you see V2 plus, okay, it's going to be this position is going to be shifted to the left. Okay, so it's difficult for V2 plus to gain electron compared to copper 2 plus. So that is you can come up with this conclusion. And you can see from the next one is going to be for reactive metal, the equilibrium lies further to the left. Reactive metal, it means they must give out electron. Yeah, so that's why you see vanadium give out the electron. Okay, they give out the electron to form more electron and V2 plus. And what are going to be the conclusion that you can draw from here? Okay, it's going to be V2 plus is going to be not going to gain the electron and form V. It's not going to happen. It means that V2 plus is difficult to be reduced. Reduced means gain of electron. I hope you can understand this. Yeah, Angela, can you understand this concept?
Yes.
Okay, so now if I ask you to summarize this one entire page over here, okay, how do you summarize this? Justin, can you summarize what is important over here? I taught you two important things.
You need to put in reduction form.
Okay. Correct. When you write the equation, put it in reduction form. Okay, what is reduction form? Electron at the left or right?
At the left, so that the right side will be
okay,
zero charge.
Okay, good. And number two, what is important that you should learn related to reactivity? More reactive metal that is more reactive.
Oh, donate more.
They are more reactive metal, they will donate electron. It means
donate more.
Electron. Yeah. So if they let go of the electron, okay, when you write the equation, yeah, the position of the equilibrium. Okay, I think your voice is breaking. I will try to continue from here. Yeah. So you see here, the position of the equilibrium. Okay, if you write, okay, if it is more reactive, like for example, this one, vanadium is more reactive. Okay, so the position of the equilibrium will be shifted to the left. Okay, to form more electron. So this one, some people will ask, sir, how to identify something is more reactive or not? This one, okay, we until now, I think in IGCSE, you memorize the reactivity series. For our syllabus, okay, you can predict. Okay, like for example, if you go down group 2, okay, we know that they have better ability to release the electron, more reactive. We predict that way. But if you want to know exact value for everything, that can be also done. Okay, that's why we are learning this chapter, because we have to refer to our data booklet. Do we need to memorize like last time, okay, reactivity series and so on? The answer is no, you do not need to memorize anymore. Okay, so you just need to follow on how to use them. This is how I am going to teach you on how to use them. Now, I will go out a bit and then I will teach you about how to use them. Okay, later, okay, when I explain, you will understand things much more better. Yeah. Now, if I have, okay, let's say I just put X, okay, X, and then I put X2 plus. Okay, X2 plus 2 electron, okay, to give me X. Okay. And then I have another one, which is going to be, let's say, Y3 plus 3 electron to give you Y. Okay. And then we are going to learn this later. Okay, I'll just put it down over here. E standard, we call it as E standard. And this E standard, okay, let's say I give you values, okay, plus 0.98. And this value, I'm going to give you minus 0.05. Okay. And I want you, okay, to look at this, okay, and analyze properly. Yeah. First thing that you need to analyze is, okay, the equations are written in form of reduction. Okay, it is written in form of reduction. That is the most important thing that you need to ensure. Yeah, it is written in form of reduction where your electron is at the left. Whether they have 2 electron, whether they have 3 electron is not our concern anymore. Okay, because this is not quantitative analysis. Okay. Because under quantitative analysis, remember we did the Faraday constant yesterday. Okay, if you have 2 electron, 2 Faraday, 3 electron, 3 Faraday, and so on. Okay, this one is not related to that. And the way they are going to be, okay, written as well. Let's say, for example, I'll give you another one more example. let's say if I have case Cl2, okay, if I have Cl2, they gain 2 electron to give you 2 Cl, for example. Okay, I just give you a value, yeah. Okay, this one I just randomly just put 0.98, for example. Always remember, this is not, okay, similar to your enthalpy change. Okay, this is not similar to your enthalpy change. So when I divide everything by 2 and I write like half Cl2 plus electron to give you Cl, you don't go and divide this by 2. Very, very important. You don't go and divide this by 2 and then you put this. This is wrong. Okay, this is electro potential. Yeah. So E cell, okay, whatever that you do to the equation, okay, it will not, okay, you do not need to divide by 2 at the potential difference. That is very, very important. What will happen if I write this in this form? 2Cl, okay, 2Cl minus, okay, 2Cl minus, okay. When I rewrite this in this form, Cl2 plus 2 electron, or I write Cl minus, okay, to give you electron plus half Cl2. Okay. Now, if you only, you turn around the equation, okay, if you flip the equation, they will be affected. How? They will be affected. The E cell now it's going to become negative 0.98. This is very, very important. It means if you go this side, then you turn it, of course, they have to go negative. Okay. So the thing that will change is only the negative part. Okay. Even this one, the E cell doesn't matter. You divide by 2 or what? The moment that you flip the equation, okay, it means the E cell is going to be negative 0.98. Okay, this is very, very important. Okay, now I come back over here. What you need to remember over here is, okay, if I compare these two cells, okay, if I want to compare these two cells, okay, of course we will compare these two, and then we will have half cell and another half cell, then we combine. Okay, so when we compare, there will be one will be losing electron, another one will be gaining electron. You cannot have both of them gain electron. Doesn't make sense. Okay, they are not going to be redox reaction. So how do I determine which one will lose electron, which one will gain electron? This is very important. You compare the value. Do remember the first step is make sure they are in reduction form. Okay, make sure they are in reduction form. You compare the E value. The one that is going to be positive must go to the right. Always remember this. The one that is going to be positive must go to the right. 0.98 is positive, negative 0.05 is negative, positive go to the right. So what will happen to the next? They will automatically go to the left. Okay, they will automatically go to the left. So when I rearrange them, x2 plus 2 electron to give me x, E value still maintain plus 0.98 work. Okay, you maintain. But this one go to the left, right? So I don't want to use left, right? So they went to the left, okay? They went to the left. So I write the equation y, okay? It's going to change into y3 plus 3 electron, okay? Erlin, what is going to be my E value now if I write in this way?
It's going to be positive. Very
good. Okay, earlier was negative. Now I flip. It's going to be positive 0.05 volt. Okay. Now, in half equation, okay, half equation. When you want to write the full equation, what we need to do, we need to make the electron the same. Yeah, so what we do, okay, we times this, okay, by 3, okay, we times this by 2, okay. So what will happen, okay, is going to be 3x to the power of this one, okay. 6 electron and 6 electron left and right will cancel, okay. So this one times by 2, times by 2, times by 3, times by 3, yeah. So I will write down this one plus 2y, okay. And it will give me, okay, 3x plus 2y 3 plus, okay. So if I compare, electron is gone. This is the full equation. Okay, so what will happen to the E value? When I do this, do I plus or minus? Jordan?
Plus.
Yeah. Then only left and right will cancel. Yeah. So it means you do the same thing. You plus over here. Your T total will be 0.98 plus this value. And you will get the answer as, okay, 0.98 plus 0.05, okay, 0.13. Okay, I think so. No, 1. Someone help me. Okay, I'm thinking.
1.03.
Okay, so 1.03, yeah. Okay, so 1.03 okay, volt. This is going to be what we need to know. Yeah. So now, yeah.
I don't understand how the redox reaction will change the electrode potential.
Okay. Why we need to change the electro potential? Do remember just now I told you you have to flip it, right? Okay, we have to flip it. Okay, so because it's an electrolysis reaction. Okay, do remember there will be one cell here, another one cell here. There will be salt bridge, remember? And then there will be one electrode potential here, one electrode potential over here. Then we compact. Okay, so one will be undergoing reduction, another one will undergo oxidation because it's a redox reaction. Okay, so we need to, like for example, maybe this one is X, this one is Y, something like that. Okay, so I will go through it. Does it answer your question, Josh?
So there's no battery involved here?
Okay, of course, it's an electrolysis, so there will be battery involved.
Okay.
Yeah,
but then
electrolysis.
How does the redox reaction change the electrode potential?
This one I will discuss after this. Yeah.
Okay.
So it means now, okay, do remember, okay, if I have, for example, if I have copper, okay, and then remember we did this experiment, copper and copper with the same electrolyte, okay, then we did this experiment and then there will be potential difference, okay. But, okay, if let's say you change this into zinc, for example, you cannot use the same electrolyte. Okay, what will happen? You need to separate them. Copper, put it one side, you put copper sulfate. And this one, you put zinc, and you must put zinc sulfate over here. Okay, and you need to make them connected. You use salt bridge. Okay, and then there will be like this. Okay. So if you put the voltmeter, you can measure. Okay, you can measure. The potential difference can be measured between two half cells. Okay, so now I will come back. Okay, it's okay if you don't understand now. Okay, you will be able to understand more. You see, this is going to be, if you look at electrode potential, okay, the position of the equilibrium differs for different combination of metals placed in solutions of their ions. Okay, it means if I have one cell here, another cell here, refer to the picture, just picturize the picture in your brain like what I draw just now. It can be either the electron can move from here to here or the electron can move from here to here depending, okay, on the type of metal electrode that you use. Okay, it depends on that. Okay, so we cannot measure directly the electric potential or the voltage of the metal and metal ions in solution. What does it mean? It means that I cannot have, okay, I put this and then I put copper sulfate and I cannot put over here copper, okay? And then I cannot just measure the potential difference of this directly by having only one cell. Impossible, okay, impossible. So what you can do is you can measure the difference in potential between metal and metal ion system. It means if you have this and this, okay, there will be two systems, okay, and you can compare, okay, you can compare. So this is what I told, okay, let's say, for example, if you call me, Mr. Gopi is fat, for example, okay, Mr. Gopi is fat. You must refer, okay, you are comparing me fat in comparison to what? It means you can say Mr. Gopi is fat compared to Newan. Okay, so Newan is going to be the standard, is the reference. Okay, he is going to be the reference. So you cannot just say, you compare just and then find out the potential difference of this. No, you need to compare with another cell. And the cell that we will use is called hydrogen electrode. Okay, it's called hydrogen electrode. So basically hydrogen electrode is Newan. Okay, you compare. Okay, you compare. So every single one person over here, when we compare with Newan, we can say, okay, Mr. Gopi compared to Newan, okay, Mr. Gopi is very fat. Maybe give a scale, yeah, maybe 10. Then compare Justin and Newan, okay, maybe not so fat, maybe give 5. Okay, something like that. Okay, that is going to happen, okay, when you try to compare with all the electrode potential. Okay, when you do that. And it is compared in terms of standard hydrogen electrode. And standard hydrogen electrode is going to be taken as the potential difference is going to be the E cell is 0.00 volt. Okay, it's going to be 0.00 volt. So just imagine Ne1 is 0. Okay, Ne1 is 0. Hydrogen cell is also 0. Okay, so if I compare, there is a value, that value belongs to, let's say, for example, if I compare with hydrogen cell, okay, and then I have a value, that value belongs for copper cell, something like that. Yeah, you compare, okay. So now, okay, this one no need to discuss, I'll just tell you, yeah, what is the reason, okay, why we cannot determine, okay, the electrode potential directly, okay, it's because of what we call as electrical double layer. Now, what is electrical double layer? Okay, if you have copper sulfate and you put with electricity, okay, what will happen? If this is copper, okay, the copper, okay, they will give out, okay, copper 2+, and then, okay, you are going to have a lot of electrons over there. So electrons will be here, and a lot of copper 2+ will be here. Okay, so electrons will be here, and a lot of copper 2+ will be here. Okay. Now, at the surface, nearing to the surface, okay, nearing to the surface, there will be a lot of copper 2+, right? So copper 2+ is there, copper 2+ is there. Okay, because of this electricity, okay, there will be a potential difference that will exist, okay, between this copper and copper 2+. Okay, that is why, okay, we say potential difference. Okay, but I cannot go and bring the voltmeter and put it over here. Cannot measure. There will be potential difference, but I cannot measure. Okay, but you can measure, okay, if you compare with hydrogen, okay, and you put voltmeter, this is 0. If there is a value here, then I can say this is the value for this. Okay, I hope you can understand. So what is electrical double layer? Electrical double layer, okay, is going to be, there will be a double layer, okay, between the charges, okay, and the electrode, okay, that will exist, okay, that will cause potential difference. Okay, you can refer to page 279 according to the old textbook, but it's not that important. Yeah, it's not that important. Yeah, but they have mentioned it in one paragraph, right? Now, so let's move on, okay, to standard hydrogen electrode. Mr. Gopi have been telling, NE1, or standard hydrogen electrode. What is that? Yeah. So how do I, okay, instead of just simply drawing as hydrogen like that, okay, there is a proper structure, yeah, for the reference electrode. So you need to know how to draw this. Okay, must know, yeah, must know. Okay, everyone should know how to draw this. Okay, this is going to be, you are going to have a platinum wire, okay, to conduct the electricity. And you are going to have this is called black platinum. Okay, what is platinum wire and suddenly black platinum? Do they have white platinum? No, actually black platinum is going to be finely divided platinum. So basically they are going to have more surface area. Okay, more surface area that will come into contact. Come into contact with what? Okay, do remember it's a hydrogen cell. Okay, there will be hydrogen gas will be supplied here. Okay, and you will have a gas tube. Okay, this is a gas tube. Okay, hydrogen will come in. So it means there will be hydrogen here. Okay, and if I'm talking about hydrogen, it means we are talking about hydrogen. There must be H plus, so H plus 2 electron. Okay, to give you H2, right? It means there must be H plus. Okay, so if there is H plus, it means the electrolyte must be something with H plus. Okay, you can use hydrochloric acid, you can use sulfuric acid, as long they are strong electrolyte. Yeah, you can use them. Okay, and then make sure the platinum electrode come into contact with both hydrogen. Okay, it is upright, so half of it with hydrogen. Okay, another half must come into contact with H plus. Okay, that's why it's half and half. Okay, so they come in contact. Okay, they must come into contact. Okay, with both H2 and H plus. And what is important over here, when they are reacting, okay, they will give you hydrogen gas. Okay, they will give you hydrogen gas. So there should be some hole, a small hole over here. Okay, there should be a small hole over here that will allow the hydrogen gas to escape. Okay. Now, what is important over here is don't simply put the hole anywhere. Okay, you don't go and put the hole over here. Okay, if you put the hole over there, whatever hydrogen come, they will go out. Okay, you want the hydrogen to react. Okay, and you want it react with H plus. Okay, you want the electron and so on react, and that hydrogen go out from here. Okay, that is the reason why the hole is at bottom. Yeah, you need to, why I'm explaining this, because you still need to draw. Okay, make sure you know how to draw. Okay, do you need to actually mention all this? Actually, no need. Yeah, so you just need to draw this structure. You need to mention about platinum wire. You need to mention about hydrogen supply. Okay, you need to mention about platinum electrode. You must mention that, okay, this is what we call as standard. What is standard condition? 25 degrees Celsius, 1 atmospheric pressure. So make sure, okay, this is done at 1 atmospheric pressure. They didn't say about, okay, the temperature, but yes, it's 25 degrees Celsius. Standard. You do not use simply any concentration. You must use 1 mole per dm cube. The electrolyte that you use must be 1 mole per dm cube. Always remember that. Okay, it means not only here, it means every single time when you say standard reduction potential of something, it means you must use 1 mole per dm cube if you compact. Yeah, it must be under standard condition. So this is only half of it. Okay, this is only half of it. Okay, the remaining half, okay, if you want to measure, yeah, you need to connect this, okay, and then connect with the remaining half. Okay, and then you put the voltmeter, and then you will get the answer. Okay, So this one, okay, you must know. Okay, you must know. So you can see here, what is platinum black is finely divided platinum. You want the reaction to happen fast. Okay, and then write the equation and so on. Yeah, I think this one all, yeah, I already discussed with you. Yeah. Now, so let's look at electro potential and redox reaction. This is what I taught you already. You see, electro potential gives us indication on how easy it is going to reduce a substance. Okay, the more positive, okay, it is easier to reduce the ion to the left. You see, very difficult. All these are taken from your textbook. But if you follow what I taught you, positive, go to the right. Okay, if it goes to the right, this is going to gain electron. Reduction is gain electron. Ag plus can reduce easily. You see, it's much more easier to understand. Okay? It's way more easier to understand if you follow what I teach. The metal on the right is relatively unreactive. Why? Because it's positive, it's moving to the right. Metal supposed to be losing electron, and they are not losing electron. Definitely they are unreactive. Okay? And how about this poor reducing agent? What is this? Reducing agent is something that will reduce others, but they themselves will get oxidized. What is oxidation? Oxidation is loss of electron. Can metal lose electron easily here? The answer is no, because it's moving to the right. So it's a poor reducing agent. Okay, everything, okay, if you follow what I say, okay, is going to make sense. But if you read directly here, okay, good luck for you. You will not understand a single thing. Okay, everything will take additional time to understand. Every single sentence. Okay, that's why I teach you first. Okay, then I'm relating it. Yeah. Now, if you look over here, the more negative value, you see negative. Negative, go to the left. Okay, if it is going to the left, okay, you see here, they say more difficult to reduce the ion. You see here, they are not going to gain the electron because they are going here. Okay, so it's of course more difficult to reduce. Zinc 2 plus. And then the metal on the right, you see here, they are losing electron. So of course they are more reactive. More reactive. Okay. And then if they're losing electron, okay, you see losing electron is what? Okay, oil rate, oxidation. Oxidation is losing electron. Okay. So what is it reducing agent or oxidizing agent? The answer is reducing agent, because reducing agent will reduce others, but they themselves will undergo oxidation, which is zinc is undergoing oxidation. So it's a very good reducing agent. No need to memorize anything over here. You just need to apply. Okay, just need to apply. And if you look at the question over here, this is another thing, you know, when you refer to this, okay, if you don't understand a single thing that I taught you just now, you won't be able to answer this. Okay, you won't be able to answer this. And you will see how things are going to be much more easier to identify now. Yeah. So you see, refer to the list. Okay, you have 5. Okay, and you see all of them are written in form of reduction. Okay, all of them are written in form of reduction. And you can see out of this, okay, this and this is positive. Okay, this 0.8 and 0.34 is positive. So if you compare between equation number 1, okay, and equation number 3, okay, if you compare, which one will move to the right? Okay, which one will move to the right? Ella, equation number 1 or equation number 3?
Both, but one is more to the right.
Yes. Okay, if I compare 1 and 3, not both. The answer is not both. If I compare 1 and 3, the one that is more positive will go to the right. Okay, so if I need to always compare. So it's not necessarily must be one positive, another one is negative. It can be positive, positive. It can be negative, negative. It can be positive, negative, negative, positive. Doesn't matter. Okay, as long as, okay, the one that is more positive, they will move to the right. So you see here, if I compare this, and even if I compare with everything, the one that will tend to move the most to the right is going to be the first one. Okay, the one that will move to the right the most. If I compare with the others, you see a negative, negative, negative. The one that will move to the left the most, Dylan, which one do you think will move to the left the most?
The fifth one?
Yes, equation number 5, negative 0.76. So I'll just put this one move to the left. Now, let's see. The others, yeah, 2, 3, and 4, they are like if you have a class and you have 5 students and you have a race, okay, the race was won by student number 1, and the last student is going to be student number 5. 2, 3, 4, they are in the middle. Okay, we don't worry much about that. Yeah. So now, which metal in this list is going to be the best reducing agent? Okay, let's see how to answer this. Reducing agent is something that will reduce others, but they get oxidized. What is the meaning of oxidation? Oxidation is loss of electron. Which of them have tendency to lose electron more? Is it silver or is it zinc? Ashley?
Fifth one, zinc.
The answer is zinc. Which metal ion in this list is the most difficult to reduce? Okay, what is reduce? Reduce is gain of electron. Which one will have difficulty in gaining electron? You see here, easily can gain electron. Everything is moving to the left. Difficult to gain electron, the most. So the answer is going to be zinc 2 plus. Kenneth, can you follow me or not?
Yes, sir.
Which metal in this list is the most reactive? You see here, metal. All these are metal. I want to find which one is going to be most reactive. Reactive means ability to lose electron more. So Kiara, which one can lose electron more?
Zinc.
Zinc. You can see zinc is losing the electron, going to the left. Zinc. Which metal ion in this list is easiest to reduce? What is reduce? Reduce is gain of electron. Okay, which one is going to be able to gain electron easily? Of course, the one that goes over here, this one. Simple. Okay, quite simple. Okay, you just need to know how to apply. The more positive, go to the right. The one that is going to be least positive or negative, it will go to the left. Yeah. So now let's try some application. How to apply? Yeah. So let's say now I have blah 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 blah. I have blah 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 blah. Okay. So it means there is going to be standard reduction. Yeah. And then the E value. Okay. E value. E value. This is going to be negative 1.07, negative 0.08 volt. Can you tell me between 1 and 2, which one will go to the right? Raphael?
Number 1.
No, 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 no. Think properly. Angela? Of course, yeah, if I say no, then the answer is 2. Yeah, why 2, Angela?
It's more positive.
Yeah. You see, Raphael, the reason why it's wrong is going to be more negative. This is more positive. Okay, if you put the number, yeah. Okay, if this one is going to be negative 1.07, this is negative 0.08. Okay, this is more positive than this. Okay, so the one that is going to be negative 1.07 is more negative. So it means they will go to the left. This one will go to the right. This is very, very important. Okay, I will come back again here. Now, This is how, okay, you can see a setup, yeah, how they have set up, okay, two different cells, okay, and they are not identifying the E cell of copper, they are not identifying the E cell of zinc. Now they are combining this cell, okay, copper cell and zinc cell, and then they want to find the potential difference between these two, yeah. So it means they're comparing, okay, it means this is when you have different metals, okay, just now when we started different metals, okay, the electrode, they will have different potential. Okay, they will have different potential. Now, you need to know, okay, where the electron goes. Okay, it can be possible, you know, the electron can go from here to here, or it can go from here to here. I don't want you to tell the electron will swim all the way here and then come over here, climb, jump, and come back over here. No. Okay, electron will not do that. Okay, the one that will move around the salt bridge is going to be the ion. Okay, electron will only move, okay, in the external circuit only. Yeah, so let's find out whether, okay, the electron will move from right to left or left to right. Okay, I'll teach you how to identify that. Later we can actually read together. But you see here, if I have copper and zinc, okay, if I have copper and zinc, you go and look at your data booklet and you will get this value. Okay, and everything is written in form of reduction. Okay, now you look at these values. Okay, number 1, number 2. Okay, so Lindsay, are you there?
Yes.
Maybe. Okay, Lindsay, can you tell me, okay, number 1 and number 2, which one will move to the right? 1 or 2?
1.
Okay, 1 will move to the right. So number 2 will move to the left. Okay, so how do I write now? Okay, remember like just now what I written. Okay, I will write down, okay, this one is going to be copper 2 plus 2 electron to give me copper. This is plus 0.34. Okay, and then this one is going to the left. I will write down zinc. Okay, it's going to give me zinc 2 plus 2 electron. Now, because I changed the position, this is going to be positive 0.76. Okay, now from here, Justin, can you tell me which one will lose electron? Based on the equation. Which metal, which electrode will lose electron?
The
Here.
well, no, the zinc.
Yeah, you can see here from the equation itself, zinc is losing electron. So it means that zinc, the electron will come out from zinc and go here and go here, and then drop over here. Then maybe jump over here, jump over here, jump over here, jump over here, then come back over here. Okay, that is going to be the movement, okay, of the electron from zinc to copper. Okay, it means what will happen to zinc? Dylan, observation, yeah? Let's see. If you look at this, okay, after maybe 10 minutes, Dylan, what you might observe?
It will dissociate.
Yeah, okay, probably it will dissociate. Okay, probably only here, because there is also zinc, 2 plus here. Okay, probably, yeah, probably. Okay, but there is also zinc 2 plus here. Okay, doesn't matter. Okay, and then you can see the copper is being kind of formed. Okay, so maybe you might have extra copper. Okay, you might have extra copper. Okay, that is going to be your observation. Okay, that is going to be your observation. And what is going to be the voltmeter reading? Simple. Add these two. You add, right? So you add these two. Okay, you will get, okay, 1.10 volt. Whatever that they explain over here is all summarized with my lesson. Okay. If you want, you can read. Yeah, you can read. Okay, but if you follow what I taught you, okay, it will be much more easier to understand. Okay. The same can be applied for everything over here. Okay. And there will be some, like for example, you see here, if you have, okay, silver nitrate, okay, you have this zinc chloride, okay, another half cell. Okay, it means I have zinc, and then I have zinc chloride here. And then I'm going to have another half cell, and then there will be a salt bridge, okay, connecting. Yeah. So why? Okay, because this salt bridge, normally what we do, we normally dip it, okay, with maybe like potassium nitrate. You see here, okay, I have added these notes from the textbook. A salt bridge is used to complete electrical circuit to allow movement of ions, not movement of electrons. Yeah. Okay, so that the ionic balance is maintained. Okay, so salt bridge do not allow movement of electrons. Salt bridge can be made from a strip of filter paper, okay, soaked in solution of potassium nitrate. Potassium nitrate, sodium nitrate, okay, these are going to be the common solutions that we will soak the filter paper and then use it as your salt bridge. The question over here is, why you don't use silver nitrate? Okay, why you don't use silver nitrate? Why you use potassium nitrate? Why you use sodium nitrate? Why you don't use silver nitrate? The answer is quite simple. Silver nitrate, okay, when the ions over here is chloride ions. Chloride ions will start to move. Jump. But after that, they will stop. Why they will stop? Because, okay, silver ion, they will join with the silver nitrate. They will give you silver chloride, a precipitate, a white precipitate. If you have precipitate, just imagine there's a big rock or big stone blocking the way of the movement of ion. What will happen to the circuit? The circuit will break. Okay, the electrolysis will not continue. Okay, that is the reason why we don't use silver nitrate. Okay, you can see it can form a precipitate. And write half equation and so on. This one, please go through yourself. Yeah, how to write the equation. Okay, how to write the electrons balance and so on. Please go through. Okay, so what we have done today, okay, is going to be this one. Yeah, standard electro potential. Okay, what is standard electro potential? Yeah, standard electro potential is measured, okay, using hydrogen electrode as another half cell. You compare, it must be under standard condition, 1 mole per dm cube. Okay, the ions, okay, 25 degrees Celsius, 1 atmosphere. Yeah, so we call it as E standard. Okay, whatever value that you have over here, this is called E standard. Okay, so something like that. So here, okay, if you look over here, there are different types, okay, of ways to measure standard electrode potential, which we will discuss tomorrow. I don't think so we will discuss tomorrow, because even when I was discussing this, it's already took us about how long? 1 hour. Yeah, 1 hour. So I don't think so. Okay, we will go through this again. No. Okay, tomorrow, okay, I will repeat whatever things that I said, yeah, in today's lesson, okay, and then I'll create because Thursday is my lecture time, yeah, so I will go through that lecture with you, yeah. So after that, on Friday, okay, we will do this measuring standard and electrode potential, because when we measure, there are different ways to measure. The common one is metal and metal ion, okay, the common one is metal and metal ion. You see this one, hydrogen cell, yeah. So this is metal and metal ion, no problem. Okay, metal and metal ion. We also have, okay, non-metal and non-metal ion. How? Okay, forget about this. This one, every time it must be standard, right? And then this one is the non-metal, Cl2. Okay, and then the ion, it must actually have the chloride ion. So you see, something similar to this. This is non-metal and non-metal ion, if you compare. And we have another setup, which is going to be ion and ion. Okay, ion and ion. So how? Okay, you put both of the ions together. Quite simple. Okay, Fe2 plus and Fe3 plus. Put all of them together. Okay, so whatever way, okay, there are 3 ways to measure. Whatever way that you do, yeah, the concept is still the same. Okay, the concept is still the same. You will get a value. Okay, probably maybe tomorrow, if I have time, I will just discuss everything. It's not going to be too long and it's not going to be too difficult to explain. Yep. So we will continue. Okay, tomorrow we will continue from the questions. Not tomorrow, yeah, Friday. Yeah, we will continue from the questions. Okay, so maybe on tomorrow, okay, I will just maybe finish up to ion cell, half cell. Yeah. So yeah, for you it will not be fast because we have done it. Yeah. For the other campus, yeah, maybe it will be fast. Okay. So of course I need to remove certain things. That's why I don't want to give you this today. Yeah. I don't want to discuss a lot of things. Okay. So probably I will remove certain parts. Okay. For tomorrow. Okay. That's it from me. Okay. That's it from me today. You do not need to wait for my notes. Okay. All these notes are taken from your textbook. Yeah. So you can refer to the textbook directly. Yeah. While waiting for me to finish the PowerPoint. Yeah. So if I finish by today, yes, I will. By tonight, I will just send it to you. Yeah. Any questions? Okay, it's already 2:30. Josh, what we have learned today?
Electrode potentials are like somewhat a measure of like how reactive the metal is when you try to put in like in electrolysis, and then like it.
Yeah. Continue, Josh.
Wait, sir, my screen is black. Hold up.
It's okay. We can hear you. Just continue.
Okay. Then for electrode potentials, if it's more positive, it's more likely to go to the right side. Wait, right, left, right. Hey, wait.
Positive to the right.
Yeah, it's more likely to form not ions, the solid cell. And then if it's negative, it's not as likely. Wait.
I think that's all. Yeah, maybe I'll just cut you off. Yeah, so we don't have time. You might have another lesson. You see here, two things very important for today. One is positive, go to the right, negative, go to the left. Okay. Second is to be able to draw the standard electrode cell for hydrogen. These are the two things that really I want you to focus today. Yeah. If you focus that, then you try all the examples that I've shown you. Tomorrow, when we do that revision, yeah, you will understand everything. Yeah. So then we can try some questions. Tomorrow, we won't even have enough time to go through the question. You saw, okay, what are the things that I'm going to cover? Whatever that I took for 1 hour with you, I'm going to cover it in much more faster manner, plus with the things that I didn't cover towards the end. Yeah, so tomorrow I will go very fast also. Yeah, but for you should not be a problem. But for different campus, I hope their teachers went through this with them. Yeah, but I will do it. Yeah, so that is going to be tomorrow. Okay, that's it from me. Okay, if you have any questions, yeah, you can just message me, then I'll try to answer you later. Yeah. Okay, see you guys. Bye.
Thank you, sir. Bye, sir.
Bye, sir. Thank
Thank you, sir. Bye, sir.